Welcome back. So we are going to continue with our discussion about linear regression, and we are going to go back to using our COVID-19 data that we have here. And we've already looked at a scatter plot, and we've already actually done the linear regression. You may not have noticed that we did it though. It's when we looked at the correlation coefficient. We had to do the linear regression to get R. But let's go back and do the linear regression again now that we know how the equation works, what things represent. Let's actually find the best fit line equation for this data set. So we go to Stat, Calc, and down to number 8, linreg a plus bx. You could do linreg ax plus b, but it really doesn't matter. As long as you know which one's the intercept and which one's the slope, it's fine. But usually the slope goes at the end. We usually put the intercept first, so that's why I use number 8. But either one is okay as long as you don't get the parameters mixed up. My x list is L1, my y list is L2, my freak list, I'm just going to leave that blank. I don't really care about storing the regression equation anywhere because I don't really care what it looks like. But I will calculate this, and it gives us this. And so we can use this. These are the two parameters, the intercept and the slope. We can construct our regression equation. But I'm going to need to do that at my board, so give me just a sec. Okay, so we need to remember which variable is which here. We've got our information down here. We know that the estimated regression line is y equals a plus bx. We just need to fill in the information for all of those variables. So we've got y is deaths. And remember, we are estimating the number of deaths. We're estimating the value of y based on what x is. So this is deaths hat equals a, the calculator tells us, is negative 4.39. You don't have to use the decimal all the way out to like the 8th place like the calculator does. We're not going to be able to do like fractional deaths or anything like that. And maybe I'm being lazy, but I'm not really taking into account that these are hundreds and how many decimals we need to go out to estimate to the nearest single death. I just go to the hundredths place usually unless I have a good reason not to. All right, so we've got A plus B is 0.65. 0.65 times X, which is cases. And I usually put that independent or explanatory variable in parentheses just to highlight the fact that this is what the X variable is. So remember, anytime you write a regression equation, an estimated regression equation, you're filling in the actual variable names for X and Y. If I see you write an equation for a regression line that has just Y hat and X here, I'm going to make a comment that says, make sure those variable names are there. It's not just to make it convenient for you to remember what the variables are. That's the way it should look. It's actually not particularly correct if you just have X and Y there. So it's important to put those there. So this is our line. And if we wanted to really put the number of deaths is really in the hundreds, the number of cases in the thousands, you don't have to put that there. That is just a convenience thing. So let's see what we can do now that we know this equation. Pennsylvania had approximately 91,000 positive cases. 91,000 positive cases as of the date that I made this data set, which was 6/30/20, June 30th. How many deaths does the model predict for Pennsylvania? So we've got an individual state that we knew had 91,000 positive cases. And we want to be able to use this regression equation to estimate the number of deaths or to predict the number of deaths based on the 91,000 cases. So go ahead, pause the video for a second, plug that number in, see what you get for estimated number of deaths. You plug in, hopefully not 91,000. If you plug in 91,000 here, you're going to get a very big number here. Remember, the number of cases in this equation is in thousands already. So 91,000 becomes 91, right? And so if you plug in 91, you get 54.76. So does that mean we estimate 54.76 deaths? To see if that makes sense, you would probably have to know a little bit about how many deaths are reasonable for a number of cases for COVID-19. That would be extremely low. And that's because the number of deaths is actually in hundreds. So we actually have to multiply this by 100 to get the number of cases we predict, or the number of deaths we predict. So 54.76 times 100 is actually 5,476. So the model predicts 5,476 deaths in Pennsylvania. $5,476. All right. But Pennsylvania, the true number of deaths in Pennsylvania is, or was, 6,650. Okay, so the model would predict 5,476 deaths based on the number of cases. But the actual number of deaths was 6,650. So how does the observed value compare to the predicted value? How does the observed value compare to the predicted value? So you can think of this as like, if we have the scatter plot, then the line, right, goes up like this. The line predicts 5,476, but the true data value, the point on the scatter plot that represents Pennsylvania, is actually up at 6,650. So the line goes below the point. The point is above the line. How far is that point above the line? Well, we could just take the two numbers and subtract, right? We could take the observed value minus the predicted value. So that's going to be 6,650 minus 5,476, which is going to be I've always got one handy, just in case. It's very useful. 1,174. So, what can we say there? We could say the observed number of deaths is 1,174 higher than the model's prediction. The observed number of deaths was 1,174, higher than the model's prediction. Is that a problem? Well, I mean, it would be nice if our model was accurate. It would be nice if this difference was 0 and that the point was on the line. But we understand, we've already seen the correlation value for this data set. It's not equal to 1. So there are going to be some differences. There are going to be points above the line, there are going to be points below the line. This point is above the line. So it's okay, the model's not perfect. There's almost always going to be some distance, either above or below the point from the line. And that's okay. So it's okay that this difference isn't 0. And in fact, we actually have a name for the difference between these two values. We call it a residual. We call this a residual, and its calculation is quite simple. We take the true value of the response variable, which in this case is deaths, right? That's the y. The true value is y. So that would have been the actual number of deaths in this example. And we subtract the predicted value of that variable. So the y hat, that's the number of deaths the line tells us. It's the predicted value, which was the 5476 we got when we plugged the number into the equation. So the difference between the actual and the predicted is called the residual. And it's because it's what's left over. It's what's left over once the model has been run. So, just for the purposes of your notes, you might want to write those off to the side there. Y is the observed or true value. Y hat is the predicted or model value. You could also think in terms of a scatter plot. Y represents the point, the y coordinate of the point. Y hat represents the y coordinate of the line at that particular x value. So, there are, well, most of the time, there are two possible outcomes when you calculate this difference. You could get a positive difference or a negative difference. You could get a difference of 0. That's not going to happen very often. So, if the residual is positive, what does that represent? Well, it means that y is greater than y hat, right? That's the only way for this to be a positive difference. If y is greater than y hat, that's what happened here, right? It means that the observed is greater than the predicted value. So that means that the point is above the line. If we think of the scatter plot. Okay? So if we were to think of a scatter plot down here, and let's say that's the estimated regression line. If the residual is positive, that means that point is somewhere above the line. And the residual is going to be whatever this distance is. The vertical distance between the dot and the regression line. So the point is above the line, and that means that the model, if this difference is positive, it means the model is underestimating the true value. So the model is underestimate. Okay. So if this difference is positive, the point is above the line, and that means the predicted value is lower than the true one. So the model is underestimating the true value. A lot of students tend to get that confused because they think if the residual is positive, that means the model is higher. But remember, it's observed minus predicted. So if you need to draw that scatter plot to interpret your residual correctly, just a nice quick sketch, that's a good reminder. The model is actually underestimating if the residual is positive. Conversely, if the residual is negative, the point is below the line, and your model is an overestimate for that point. Okay. So if the point's above the line, you've got a positive residual, and the model's an underestimate. If your point is below the line, that's a negative residual, and the model is actually overestimating the true value. So, looking at an individual residual, you can calculate it as long as you have the true observed value and the predicted value from the model. You need both to calculate the residual, right? So the type of problem is common where you're either given this or asked to calculate it from raw data using your calculator. You get the model, you're given a true value for an individual, and it asks you to calculate the residual. It's that simple. Just take the difference. Plug that number into the formula, get your predicted value, take observed minus predicted. Pretty simple. But where residuals really come in handy is when we look at all of them together. So we can actually calculate for an entire scatter plot, not just a couple points, we can calculate the residuals for every single point together. Some residuals are going to be positive for points above the line. Some residuals are going to be negative for points below the line. But when we look at the residuals together, it can tell us a very interesting story. It can even tell us whether doing linear regression was a good idea in the first place. So, to talk a little bit more about residuals, we need to go back to our calculator, which means I need to go back to my desk. All right, let's take a look at what is called a residual plot. We're actually going to take all of the residuals for every data value for every state in our data set and look at the residuals together and see what they look like. In order to create a residual plot, we need to go to second stat plot, right? Because it's a plot just like any other. We're going to turn on plot 1. It is a scatter plot, so we're going to look at it like that. But instead of graphing L1 versus L2, we're actually going to keep the x list as L1. So this is still the x variable. But the y on the vertical axis, instead of looking at the y values, we want to look at the residuals instead. And the great thing is, remember when we ran the linreg at the beginning of the video? Anytime you run a linear regression on your calculator, it stores all of the residuals automatically in its own list. So instead of L2, we need it to find the residuals list. So where that is, it is at second list. So that's going to be second, and then see how it says list here in blue? Second list. And it's got the names of all the lists, and then the last one here is resid. That's the list of residuals. So we will go down there, enter, and now we're going to be graphing L1 versus the residuals. This is going to let us see what those residuals look like together. So, the mark is fine, color blue is fine. Zoom 9 again for zoom stat, and this is what our residuals look like. Interesting. So what you're seeing here is on the x-axis are the same x values as before. So in our COVID-19 data set, the x variable is the number of cases in thousands. That's still the same thing on the x-axis. But on the y-axis is the residuals. So it's the observed minus predicted for each state. So you see some are above 0, some are below 0. And just looking at this window, like, all these tick marks are really bothering me. Let's do the X scale by 10s and the Y scale by 10s, just to make it look a little less chaotic. There we go. Whew. Okay. So we've got some positive residuals up here. We've got some negative residuals down here. Remember, this is Florida. This point was well below the line. So on the residual plot, it's now well below the x-axis. You can think of the residual plot as the scatter plot, but like flattened so that the regression line is now this line, this flat x-axis. And all the points have moved, essentially rotated with it. That's not a mathematically sound explanation, but all these points relative to the x-axis are in the same position that they were relative to the original regression line. This point is still above. It was above the regression line. Right? So this is called a residual plot. And ideally, what we want to see in a plot like this is completely random scatter of the points. That's what we would like to see. The reason we want to see random scatter of points here is because if there's no pattern to these points, then that means that after we fit the straight line to the data, there's no pattern left. We have taken care of the pattern in the data by fitting a straight line to it. That would tell us that linear regression is effective and that it's appropriate. If there's still some kind of pattern in the points after you've already fit that straight line, then that's telling you linear regression didn't really explain the shape of the data. There's something else going on. Maybe you need to fit a different type of curve or something like that. Maybe the data just can't be explained using a straight line. Okay? So this is what we use the residual plot for, is to see whether linear regression is appropriate for a given data set. So the question is, what do we see in this residual plot? Was it appropriate to perform linear regression on this data set? Well, let's take a look. Does this look like random scatter? Well, it's kind of hard to see because you don't exactly know what you're looking at. You don't have a frame of reference necessarily. This is the first residual plot you've ever seen. There are some data sets where if you fit a line to it, a straight line, and you look at the residual plot, you're going to get a distinct curved shape in the residuals. That would clearly tell you linear regression is not appropriate. There's still a curve in the data. Here, we don't see a distinct curve, but do you notice that, like, on the left side of this graph, so for low x values, for cases that, or for states that don't have a lot of cases, it's very tightly bunched. All these points are very close together. But as we go to the right, it spreads out. It spreads out like this. In the statistics world, we call this shape a fan shape. It fans out as it goes to the right. And that is actually also an issue. It's a problem that would suggest that the linear regression we did, even though the data was linear in shape, there's still increasing variability as the number of cases goes up in a state. We don't want to see that. We want to see uniform scatter across the x values from left to right. So the fact that we see this increasing variability as we go to the right is a problem. And we're not going to fix that problem yet. We will revisit regression as we go through this unit and at the end of the course. We're going to find out how to fix this, right? The important thing is that you know that a residual plot is something that exists, that you can use a residual plot to determine if linear regression is appropriate for a data set, and what you don't want to see You do want to see random scatter in these points. You don't want to see any kind of curved pattern or this fan shape of increasing variability as you go to the right. So it's kind of unfortunate we're going to leave on this cliffhanger that you don't understand what's wrong with this or how to fix it, but hey, maybe that'll keep you tuned in. So in the next video, we're going to talk more about regression and what makes the regression line the best fit line. Why isn't it some other line? Why does it have to be that one? We're finally going to answer that question in the next video. So we'll see you then.